I'm just going to look a little bit more at graphing these functions by using calculus. So finding where it's increasing, decreasing, finding max and mins, and finding inflection points and concavity. And so looking at our function in front of us, y is equal to the natural log of 3 minus x squared. First of all, it's helpful to figure out what our domain is. And so domain, I usually look at trouble spots, trouble values that I would plug in from x, and that would give me back not a real number. So we have to worry about radicals, variables in the denominator. We also have to worry about natural log. We can only take a natural log of a positive number. So what we're taking the natural log of, this 3 minus x squared needs to be greater than 0. And so kind of think back to algebra when we're solving a nonlinear inequality. This is where we found values which set it equal to 0. Those were our critical numbers, and we could test values, or we could actually graph this too. That actually might be faster. It doesn't matter. If we graph it, think of this as graphing y is equal to 3 minus x squared. I can use transformations. I know this minus in front of the x squared, that is making it so my parabola is facing downwards. If you think of this as y equals maybe negative x squared plus 3, that plus 3 outside is shifting it up 3 units. So 1, 2, 3. And it's going to be going like this. And so we're looking for all the x values, which this is greater than 0. So all the x values where this is greater than 0 is in here. And so setting this equal to 0 or factoring this, we're looking at when is 0 equal to, this is a difference of squares we can think of, like root 3 minus x, all times root 3 plus x, if you want to think of it that way. Or we could isolate x squared and take the square root of both sides. So we get x is plus or minus root 3. Okay, so that was just to find my domain of what I was taking, what we're taking the natural log, the domain of that natural log of 3 minus x squared. So my domain here are all values between negative square root 3 and root 3, not including. So we also want to find out where this is increasing and decreasing. And so we can do that by looking at the first derivative. So first derivative, we want to take the derivative of y. So the derivative of a natural log is 1 over what you're taking the natural log of, which is in this case 3 minus x squared, times the derivative of what we're taking the natural log of. So the derivative of 3 is 0. And that derivative of negative x squared gives us back negative 2x. So we just found out our derivative is negative 2x all over 3 minus x squared. So values where this is equal to 0, our derivative is equal to 0 when negative 2x is equal to 0, when our numerator is 0. So divide by negative 2, that gives us x equals 0. So that's one of our critical values. And then looking at where it's undefined. I notice it's undefined values, which set my denominator 0. That's positive root 3 and negative root 3. But notice that those values aren't in the function of our original. It's not in the domain of our original function. And so those really we're not worried about, although that when we are looking at our domain, we are looking at everything bigger than negative root 3 to root 3. And then we just found that one of our critical values was 0. So when we test a number, we're going to choose something between negative root 3 and 0. So how about x equals negative 1? So recall we're plugging this into our derivative function to see if we have a positive or a negative value. So as our slope positive, it's increasing. If our slope is negative, then it's decreasing. And so plugging this in, we have the natural log of 3 minus negative 1 squared So we have the natural log. So this is going to be 3 minus 1, which is 2. And so natural log of 2 is, I believe, bigger than 0, but let's just see. That gives us back 0.69. Okay, so this value,
Isn't the natural log of 3 minus x squared the original function?
oops, you are right. So thank you. Put the derivative, but I used the original. So we want to use this function. Okay, so this is much easier to see if it's positive or negative. So if we plug in -1, wherever we see an x here, we got -2 times -1. So that's positive 2. I don't really care what the number is again. And then if I plug in -1 in here for x, well, that -1 quantity squared is 1, but 3 minus 1 is 2. So this is also positive. And so this is greater than 0. And so that tells me that my function is increasing, at least between -√3 and 0. And so let's choose a number that is between 0 and √3. So how about x equals 1? So plugging that in, we have y prime of 1. Well, -2 times +1, that gives us a negative in the numerator. All over 3 minus 1 squared, that's still 2, that's positive. So this is less than 0. So we know that our function is decreasing between 0 and √3. So if we're increasing to decreasing, 0 is defined in our original function. So that tells me that at x equals 0, a max is going to occur. But in order to figure out what that max is, I have to plug that back into my original function. So if we go in here and we plug in 0, wherever we see an x in our original function, that will give us the point. And so we have for our original function, y is equal to the natural log of 3 minus 0 squared, which is the natural log of 3. So we have a point at 0, natural log of 3. But if I was going to graph that, I would need to know approximately what that was. So that is 1.1. This is a max. Okay, so now let's look at concavity. So concavity, we need to look at the second derivative. So let me look at this. We can leave it like this. We can rewrite it and use the product rule. But if I take the second derivative like this, I'm going to need to use the quotient rule. So it's up to us what we want to do. I don't care either way. So if we look at, let's look at the quotient rule, because today what we're going to be looking at, I want you to make sure that you don't mess it up with the quotient rule. Okay, so looking at the derivative of the numerator, derivative of -2x is -2. All times our denominator, which is 3 minus x squared, minus our numerator, which is -2x, times the derivative of our denominator. So derivative of 3 minus x squared is -2x. All over our denominator, 3 minus x squared, quantity squared. So let's simplify this down. Let's distribute that -2 inside the parentheses. So -2 times 3 Yeah, -6. -2 times -x squared. So that's plus 2x squared. And then here we have 3 negatives. So 3 negatives together multiplying is negative. And 2x times 2x is 4x squared. All over 3 minus x squared quantity squared. So cleaning this up just a little bit, we have 2x squared minus 4x squared is -2x squared minus 6 all over 3 minus x squared quantity squared. Let's pull out a -2 from the numerator. Pulling out a -2 from the numerator gives us x squared plus 3. Okay, so we're looking at, to find concavity, we want to look at values where our double derivative is equal to 0 and where our double derivative is undefined but defined in our original function. If you look at the numerator, because that's what's going to set our double derivative equal to 0. So let's set our double derivative equal to 0. So let's just look at when is our numerator equal to 0, because that's what's going to set the whole thing. Well, I'm looking for real numbers that set this equal to 0. X squared plus 3, that's not factorable over the real numbers. And if I looked at this and set that x squared plus 3 equal to 0, and I subtracted 3 on both sides and used the square root property, this is an imaginary number. Okay, so that's not real. So there's no real number that sets this double derivative equal to 0. And the values where it's undefined, well, those were the same thing as the problem we had in our first derivative. Those were values that were not in our domain. So this tells me then that my function is either going to be all concave up or all concave down. And so we just need to choose a value in between our domain, -√3 and 3. -√3 and +√3. So choosing any number in there, and we're going to plug it into our second derivative. I'm going to do it in this factored form. So how about let's just do 0. And so if we look at the double derivative when x is 0, we get -2 times 3 in the numerator. So that's -6. It's a negative number. All over 3 minus 0 squared. So 3 squared in the denominator, which is positive. So this is less than 0. And so I know that this is concave down here. So there's no value in our domain that sets this equal to 0. There's no inflection point. There's no point where it changes concavity in our domain. So there's no inflection point. And so now let's go and look at graphing this. So maybe just do it up here. Okay. So we know we have some certain points. We know that 0, 1.1 is a maximum. We know that this is concave down. We know that it is increasing. And then decreasing. And it's between -√3 and √3. So we need to see what's going on. We're going to have some open circles in here. And so for original function, let's see, square root of 3. Square root of 3. Is approximately 1.7. So let's just do that. So actually here, we can think of this as limits, right? We can look at this as a limit as x is approaching negative root 3 on the right-hand side of our original function, natural log of 3 minus x squared. So what happens here as we get closer and closer to negative root 3 on the right-hand side? We can't do the direct substitution because if we do that, we get the natural log of 0, which is undefined. So this right here is going to negative infinity. So it was shooting down. And the limit as x right here was going to positive infinity, not positive infinity, was going to root 3 for this natural log of 3 minus x squared on the left-hand side of that domain. We also saw that it was going down to negative infinity. We need to find maybe where our intercepts are, or x-intercepts. And so we can look at where our x-intercepts are by setting our y value of our original function equal to 0. So x-intercepts. So we're going to let y equal 0. And so if we let y equal 0 for our original function, we get 0 equals the natural log of 3 minus x squared. Okay, so let's just rewrite this in exponential form. Remember, natural log is log base e. And so the equivalent of this in exponential form is e raised to the 0 is equal to 3 minus x squared. Well, anything raised to the 0 other than 0 is 1. So we get 1 is equal to 3 minus x squared. If I can either use my square root method to solve, or I can set this equal to 0 and try to factor it. If I subtract 3 on both sides, I get negative x squared equals negative 2. Divide by negative 1, I get x squared equals 2. So x equals plus or minus square root 2. So plugging that into the calculator just to get an estimate of what root 2 is. I know it's between 1 and 2. That gives me 1.4. So x is plus or minus approximately 1.4. Okay, so we had asymptotes really at this negative root 3 and positive root 3. We just saw that across the axis at negative 1.4 and positive 1.4. And it was concave down everywhere. And that was our max. So basically it looks like a parabola shape in here. Okay, so putting all that together, we were able to craft that. These can get kind of time consuming, especially trying to explain.